So, I have already mentioned, is okay?
More to the right.
This way. Okay, I have already mentioned the Dirichlet problem. We have a domain omega with a boundary d omega. Omega is a bounded domain, maybe sometimes unbounded, with a sufficiently regular boundary. And we have two functions, f in, say, C2 of omega, and g in C1 of d omega. So we have one function inside and other function on the boundary. And the problem is the following. We are looking for a function u such that Laplacian u equals f in omega, and u on the boundary d omega equals g. So we are looking for a function which satisfies this boundary condition and this equation. So it's called Poisson equation. So it is all in all, there's a problem for Poisson equation. We have already a solution of this problem in case when omega is the whole space. If omega is the whole space, so we have no boundary condition. So if omega is Rn, then solution looks as follows. U of x equals integral over Rn phi of x minus y f of y dy. Where phi is the fundamental solution of the Poisson or Laplace equation. It has the following properties, that phi of x is such that its Laplacian is 0 for x different from 0. Yeah, so outside of 0, this function is harmonic function. And it has the following property. Phi of x is phi of module x. So it is spherically symmetric. You can rotate this function, yes? And the last is that, let me say, if you take the origin and take a sphere of arbitrary radius, then integral over the sphere n minus 1. Let me better use our notation as n minus 1 dimensional sphere, the center of 0 and radius r. S of 0 r. Gradient. Oh, I'm sorry, I'm writing outside the area. Integral S 0 r. Gradient phi dot no unit normal, external normal. So this is mu ds equals 1. Yeah. And in a very rigorous sense, this means that Laplacian of the function phi equals delta function, delta of x. No, in which sense? For example, we modify this function phi, convolve it with phi small delta. We have a function which is harmonic outside the ball of radius delta, and inside the delta, its Laplacian is such delta-like function which is concentrated in the ball, and its integral equals 1. Yes, and when delta goes to 0, this, so to say, mass of this Laplacian concentrates more and more to 1.0, and it's unit mass. Yeah, and again we can imagine this that we have a porous medium filling all the space, and we have a source of liquid at the point 0. Yes, and this source has unit, say, capacity. So the flux or influx of the liquid is 1. Then the pressure field is given by this function phi capital. Now, phi in the small dimensions has the following: phi of x equals 1/2 model x if dimension is 1. Yes, it is 1 over 2 pi logarithm model x if n equals 2, and is equal 1 over 4 pi minus 1 over pi model x minus 1 if n equals 3. And further in dimension n, which is more or equal than 3, it is model x minus n plus 2 times some coefficient. This coefficient just ensures that the flux of this function is flux of its gradient is equal to 1. Yeah. So this is the principles are clear from these three examples, 3 dimensions, 1, 2, 3. So if necessary, I will not write down the general formula for arbitrary n. It is just for, and we will find for practically interesting n, 1 and 2 and 3. By the way, n equals 1 is also example. So many things can be seen in one-dimensional case. So when you study some problems in or partial differential equations, sometimes and many times it is useful to look first at one-dimensional case. Now, this solution, let me write again, u of x is integral over Rn phi of x minus y f of y dy. Say that Laplacian u is f. Yeah? This solution is good, and the Liouville theorem, which I cited before, says that this solution is even unique up to adding some constant if you consider, say, f a function having compact support, so it is 0 outside some ball, and if you consider solutions which are bounded, then this solution is unique now up to adding a constant. But it doesn't help much if you solve equation in bounded domain with boundary conditions, so it is really a problem for the Poisson equation. And for this, we use the fundamental notion of Green's function. So Green's function is, I say, absolutely fundamental, and let me define it. So consider domain omega. Suppose that x is a point inside omega. And Green's function is the following thing. Consider the function phi of x minus y. So it is y1, say yn. So we are in the y space, and x is a point in the y space. Phi of x minus y, so it's a function having a singularity at the point x. This function is takes some values on the boundary, and suppose there exists a function psi of y such that first Laplacian psi is 0, and second psi on the boundary d omega equals phi of x minus y at the point psi of y at d omega. Yeah. So we find a function which has we have the same boundary values as the function phi of x minus y, but has no singularity here. And then we define a function g of xy equals phi of x minus y minus psi of y. Now here x is implicitly as a parameter which I don't write. So this function satisfies the following thing. First, g of xy equals 0 for y on the boundary and x in omega. Yeah, because we subtracted. And second, Laplacian in respect to y, g of xy is delta function x minus y. So it is a unit mass or delta function concentrated at the point x. So such function is called Green's function. So one, I would say, suspicious thing here is that suppose there exists function. Why this function exists? Yeah? Who said that this function exists? In fact, this is the central problem of all this theory, existence of solution of the Dirichlet problem, psi is solution of Dirichlet problem with the right hand side 0, nothing more, and with given boundary conditions. So anyway, these are other way we have to solve this problem, or not solve, or at least prove that solution exists. This requires harder work. And for now, we assume that such thing exists. Yeah, so now we are at say I have some debt to you to explain why such function does exist. It is very far from trivial, and in fact this problem required many years to settle. So it is a great part of history of mathematics. So suppose such function exists. And now let us make some calculation with Green's function, which will show you how to solve this equation. If you have Green's function, if we have it, then we can solve the Dirichlet problem. So to this end, I have to remind the Green's formula. Green's formula is the following: integral over omega for any two functions. Let us call these functions, say, v and w. V Laplacian w minus Laplacian v times w dx equals integral on the boundary v du d mu minus du dv d nu ds. Do you recall this formula? It is in fact integration by parts.
But before it was v and w, then it becomes
Excuse me?
v and u.
V is w minus w dv. Yes. The same function should be. Yes, it is a formula of integration by parts. To be complete, let me do it. So consider integral over omega gradient v dot gradient w dx. Yes, and integrated by parts. We can write it is v integral over d omega d dw d nu ds minus integral over omega v times Laplacian w dx. It is integration by parts. On the other hand, we can change roles of v and w because this expression is symmetric, and this is equal to integral over the omega w d v d nu ds minus integral over omega w Laplacian v dx. And now so this is equal to this, so we have to say move no, it's the same. We can to move this here and this term here. So we have integral over omega v delta w minus w delta v dx. So I moved it here, so I have to move here. Equals integral over d omega v dw d nu minus w dv d nu ds. Yes, it's the same formula. So the signs are correct. This is the Green's formula. And now let us substitute here the following function. Let us take any function u in C2 of omega, any function. No, any regular function. And so let me write this formula for this function u and u of y. And function g of x, y. So x is a parameter. Yeah? Let us write this formula. Integral over omega. So it is v, it is w. It is v. U of y delta with respect to y g of x minus y minus g of xy delta with respect to y g of y dx equals integral along the boundary v, it is g of xy d no v is u of xy u of y dw d g of x y d nu y minus g of x y du of y d nu y ds. And let us look what happens here. The function g of xy, sorry, g of xy for a fixed x in omega has the property that its Laplacian is delta function at the point x. Yes? So equals integral to omega u of y delta x minus y minus g of xy delta y u of y equals f of y. So it is g of xy f of dy. It is the left hand side. Equals what is written here. Here is written integral over d omega u of y. U of y on the omega, u on the omega is g in our notation. So it is g times d g of y, d g capital x y, d nu y, minus gxy. Gxy, when I is on the omega, we subtracted functions which has the same values as phi, so it is 0. So this time is 0. dsy. Now let us look further. Integral u of y delta function at the point x. It is the value of the function u at the point x. Yeah. So you have u of x minus integral over omega g xy fy dy equals integral over the boundary g of y d g capital of xy d nu y ds. Now what remains? It remains to bring this integral to the right, and we have the following formula. U of x equals integral over omega g of xy f of y dy plus integral over d omega g of y dg xy d nu y ds. This function depends on x and y. X is inside omega and y is on the boundary. Let me introduce notation to make it more, I would say, comprehensible. Let me write k xy equals dg xy d nu at the point y, here x in omega, y in d omega. And then our formula becomes even better. So we solve the problem. Delta u equals f in omega, u on d omega equals g. Yes? And solution looks the following. U of x equals integral over omega g xy f of y dy plus integral over the boundary k xy g small of y ds y. So y is variable of integration. Yeah. So this is the formula here. We can see all the constituents of the solution. We have that ux depends on f here, and f at every point brings some contribution to to u of x. And also we have some contribution from the boundary. So if, for example, one of them is 0, no, only one integral remains. Yeah? Both cases are important when, say, g is 0, then only this remains. If f is 0, only this remains. So this is how we solve equation. No, it is not a true solution because it remains to find this function g, capital G of xy. It is called the green function. How can we find it? In fact, it is a problem of the same level of difficulty as to find solution of the general problem. So we simply say push the difficulty from one place to other. Anyway, we have to solve it, this problem. And next, what I'm going to do next, no, discuss some properties of Green's function.
So I have a question.
Yeah.
Can you explain why the partial derivative of u with mu is 0?
Excuse me?
Can you explain why the partial derivative of u with mu is 0?
No, it is not 0. G is 0 on the
Oh,
boundary. G itself by construct. So we removed one part of difficulty. Yes. We could remove other part constructing different Green's function such that its normal derivative is 0. Yes, and then it is good to solve the equation when not the value of the function is given, but value of normal derivative, which is called the Neumann problem. Yes, but now let us concentrate on the Dirichlet problem. Okay, before we go into particular cases where we can really find the function g, xy, and kxy, let me discuss one general property of Green's function. Xy equals g of yx. Identity. So g is symmetric function. Yeah. No. For example, if you take the hydrodynamic interpretation of all this situation, we have some domain where the filled with porous, homogeneous porous medium, and this domain, say, is kept under constant external pressure, so the fluid can enter and exit freely. The pressure here is constant. Yes, and we say pump the fluid at one point x and measure the pressure at other point y. Yes? It's one experiment. And other experiment, we pump the fluid at the point y and measure the pressure at the point x. And this theorem says that the result will be the same. Yeah, which is quite strange. But the oil people say that there exists some coefficient of hydrodynamical connectivity between the points x and y. And this coefficient is symmetric, so if it is easy to pump the fluid from x to y, then it is easy to pump it back. The same for electric conductivity. So if you have an electric conductor, you have, and you put here one electrode, which will, here we keep the potential constant, here we keep potential different from potential on the boundary, then here will be some distribution of potential, electric potential, yes, and then you measure potential at the point y, and then you do similar thing, but exchange places. You put electrode to with a given potential at the point y, and measure potential at the point x. Again, result will be the same. Yeah. So this is really general property. No, in other domain it is so if you are speaking and I can hear you, this means that if I will speak, you will be able to hear me. Yeah, so there is no such one-side correspondence. Okay, but now how can we prove it? Very easily. Consider our domain omega, and here we have a point, say, x, and here we have point, say, y, and we denote the coordinates by z1 and so on zn. So the running point of omega is called, variable point is called z. Yes? And so consider the function g of x z, which let us denote it by v, and g of y z, which is w of z, w of z. No, these functions are not of C2 because they have singularity responding at the point x and the point y. Yes, but we can a little bit modify this function, regularize it, and work with regularized, and then take the parameter delta of regularization to 0, and it will be easily verified. So let us handle these functions as if they were regular. Now we have the Green's formula. Green's formula, integral over omega v Laplacian w minus w Laplacian v dx equal integral over d omega v dw d nu minus w dv d nu ds. And now let us look what it all means. Laplacian v of z equals delta function at the point x. Delta z minus x. Laplacian w of z is delta function of z minus y. Yeah. Now, integral left hand side, integral v Laplacian w dx dz equal simply Laplacian w delta function. So integral g of xz, x is fixed, delta of z minus y dz, which is equal simply g of xy. Now, integral w Laplacian v dz over omega equal integral g of yz delta z minus x, which is dz, which is equal g of yx. Yeah? It is here. And now on the right, v is g of xz. So when z is on the boundary, v equals 0. Yeah? For z in d omega. And the same for w. W is g of yz. When z is on the boundary, it is 0. So w and v is 0 on the boundary. So this means that the right hand side base is 0. Both terms are 0. Yeah? So it is 0. So after all, we have g of xy minus g of yx is 0. So this is symmetry of the Green's function. No, okay, it is all very good, but how can you find the Green's function? Let us consider today the simplest case of after the whole space is half space. Green's function in half space. So we have x equals x1 and so on xn. Let me write the following: x prime xn. X prime is x1 xn minus 1. So it's shortcut for the first several coordinates. And our omega equals the set of x prime xn such that xn more than 0. So say in the plane, it is the upper half plane. In the three-dimensional space, it is the upper half space. here we can use the trick which we already used, the reflection method. So green function in half space by reflection. So this function has the following form, the function phi. This is this upper half space. This is the point x. And the function, we can take, say, two-dimensional case, n equal to, so it is x1, it is x2. Then phi of x, y equals 1 over 2 pi logarithm model x minus y. So this function is not zero on the boundary, on the x1 axis. And but if you take the function phi of minus x, y, yeah, just substitute, equals no, I'm sorry. Minus x is here. I want to borrow notation from complex analysis. So x equals x1 xn equals x prime xn. And I define x bar equals x1 x and the last is minus xn equals x prime minus xn. So I change the sign only of the last coordinate. So if this point x, this point x bar. Yeah? And I consider the following function. Phi of x, y minus phi of x, y bar. No, if you take n equal 2, then you have, and this is g of xy. So x, this is g of xy equals 1 over 2 pi logarithm moduli x minus y minus logarithm moduli x minus y bar. Yeah. So this function, which is equal to 1 over 2 pi logarithm model x minus y minus logarithm model x bar minus y. Now, let us see when y is on the boundary, then if y is on the boundary, then y equals y bar. If y on the boundary, then y equals y bar, yeah? Because y equals y1, y2 coordinate, y bar is y1 minus y2, and y on the boundary means that y2 equals 0. So if y2 equals 0, then these 2 points y and y bar coincide. Yeah? So this means that this function satisfies the boundary condition. G x y y on the boundary equals 0. Now, the function g is harmonic function because this is harmonic and this is harmonic. Harmonic function is a function of y. It is a harmonic function. Delta yg of xy equals 0. Identity. And the only singularity is when y equals x. Yes? No, if you consider the whole plane, then there is second singularity when y equals x bar. Yes? So here was a picture, this point x, this point x bar, and the function has only this singularity because second singularity is beyond our domain. Our domain is this, the upper half plane. So the function is satisfies all conditions, and it is the Green's function. Now it remains to find its derivative when its normal derivative when y is on the boundary. So let us do it. So x is x1, x2, y equals y1, y2. So we have to consider this function x g xy equals 1 over 2 pi logarithm of, let us take logarithm of square of distance, x1 minus y1 square plus x2 minus y2 square. It is a double logarithm, so we have to divide by 2 to have the same. Minus 1 of 2 times 2 pi, the same logarithm, x bar minus y. It is x1 minus y1 square plus minus x2 minus y2 square. So this is g. Now let's differentiate the g normal derivative g dy2. dy2 equals 1 over 4 pi. Here you have x1 minus y1 square plus x2 minus y2 square. And here you have derivative with respect to y2 minus 2 x2 minus y2. Yeah? Minus 1 over 4 pi. Here you have x1 minus y1 square plus x2 plus y2 square divided by minus x2 minus x2 minus y2. Yeah. It is this. Now we have to set y1 and just a minute. y2 equals 0.
Shouldn't there be a 2?
Excuse me?
Shouldn't there be a 2 before the parentheses?
Yes, 2. Yes, equals 1 over 2 pi. So y2 is 0 times x1 minus 1 x1 minus y1 square plus x2 square. And here we have minus x2 minus x2. And here minus 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 you have again plus minus x2 and the same denominator x1 minus y1 square plus x2 square equals 1 over pi minus 1 over pi x2 x1 minus y1 square plus x2 square. Now here we have this minus 1, but look what we did. We took the derivative in this direction. Yes, d dy 2. Yeah? And normal, external normal looks opposite. So this means that d g of xy d nu y is opposite is 1 over pi x2 x1 minus y1 square plus x2 square. And this is what we denoted by k xy. equals 1 over 2 pi logarithm x minus y minus logarithm x minus y bar, and k xy equals 1 over pi x2 x1 minus y1 square plus x2 square. Here the point x equals x1, x2, y equals y1, 0. Yeah? No, in particular, if x if say y1 is 0, yes, y1 is 0, we have the following function, k of x0 equals x2 x1 square plus x2 square, 1 over pi of this. So just look, there is a homogeneous function of order minus 1. Because numerator is of order 1, denominator of order 2. So it's a homogeneous function. This function is 0 on the boundary. If x2 is 0, this function is 0. Yeah? Now it's interesting to see what happens with this function when when we approach the x1 test. So it is x1, it is x2. So k of x0 equals 1 over pi x2 divided by x1 square plus x2 square. Yeah? No, this is a function like this. Yeah? If you integrate this, integral from minus infinity to plus infinity, k x0 dx1. Yeah, x is x1, x2. Equals integral 1 over pi integral x2 x1 square plus x2 square equals 1 over pi logarithm, I'm sorry, not logarithm, arctangents of x1 divided by x2 from minus infinity to plus infinity, yes? Arctangents changes from minus pi over 2 to pi over 2. So after all, we get that it is 1. Yeah? And so, what happens when the x2 goes to 0? when x2 goes to 0, the value of this function when x1 is 0 is 1 over x2. So it goes higher and higher. But the width of this is also proportional to x2. So when x2 decreases and goes to 0, we have the following graphs of this function. This is for one x2 not so small. This is for smaller x2. This is for even smaller, and so on. Yeah. So we have these functions form a sequence. These functions, a sequence of delta-like functions. Yes. So when x2, this parameter, goes to 0, they somehow shrink in the direction and grow in the vertical direction, and the result, the integral keeps to be 1. No, they are not with compact support, so I don't say that it is the same, but nonetheless they behave like, excuse me?
Is there a class here?
I'm finishing.
Okay. Yeah, thank you.
Yeah, yes. And so we can say even more that if we solve the problem, the following problem. Delta U equal 0 in omega. Omega is upper half plane. Yes? U on the omega is delta of x1. Yes? Just imagine delta of x1. Then U of x1, x2 equals 1 over pi x2, x1 squared plus x2 squared if x2 more than 0. Yeah? So this is the meaning of the function k of xy. K is a solution of the Dirichlet problem for Laplace equation when the boundary function is delta function. No, you can imagine that it is delta-like function, and then it becomes more and more concentrated, and in the limit we get this function k. So this is the picture of this situation. Okay, so what you know what? This is material for the next program. Anyway, we have a break. So I will send you a problem because here we did it in one-dimensional case. Yes, I would like to ask you to do it in two-dimensional. To start from one-dimensional, then jump to three-dimensional for all n. So it is the homework. So we'll do it. So let's finish now. Question?
When are we going to have the midterm?
Give me?
When are we going to have the midterm?
No.
There's no midterm.
No, midterm. Moreover, I think about take-home exam because I can't imagine what we will do in the standard undergrad exam. So I think I will give you several questions which are a little higher level so that you should have some space and time to think.
So the next assignment is
Excuse me?
The next assignment is due for next.
So this assignment is due. No, it's for a week. Yeah, so it is due on Tuesday.
So when we come back.
Yes.
Okay.
Okay.
So we meet next time on Tuesday and then decide. And If you don't mind, we'll continue our meeting, additional meeting on Fridays. Yeah.
So for the final, it's not gonna be